Okay, welcome everyone. Today I would like to explain to you what is a linear subspace. Not just what is a linear subspace, it's a bit boring. We'll see, it's a very natural idea. So why is this a natural idea? So why is linear subspace a natural idea? Or why are hyperplanes a natural idea? And the whole story starts as follows. And in some sense, I would like to convince you that you could have invented the notion of a linear subspace, of a subvector space, whatever you want to call it. And the idea is as follows. So let's say somewhere, someone gave you some structure, something, a set with properties, whatever, something. It doesn't matter. And you would like to think of, okay, could be a reasonable notion of a substructure? Right? So you're given something, an object of a certain type, right? Type X, Y, Z. And I call my object a V. Of course, V will be a vector space soon, but for now, V is just an object of type X, Y, Z. So my wish list, or kind of, I would think, sounds like a good idea to have as a substructure, would be something like, I have a given structure, right? It's of type X, Y, Z. So it would be pretty good if W would still be of type X, Y, Z, right? And the three axioms kind of that you will usually see in this setup, I like to stress, this is really kind of a general idea. Substructure really should be, maybe you see groups. Subgroup is exactly what you think it should be if you follow this list. A subvector space, a linear subspace, will be exactly what you think it should be if you follow this list. A sub whatever will be exactly what you know. There are two things that are pretty silly. I mean, it's sub, right? So W should be in some sense inside of V. And it definitely shouldn't be empty because empty just satisfies everything. I don't care. Right? The third one is actually the crucial one. And the point is, okay, you have V given, maybe it's a set or whatever. And yeah, if you take a random subset, then you very likely lose the property of being of type X, Y, Z. So the main idea, the main ingredient, the main definition, the main point, said main often enough right now, is that W should be of type XYZ as well. That's why it is a substructure, not just a sub anything. It's still of type XYZ. That just means it's closed under the XYZ operations, whatever those are. Yeah, examples. What you will see, what we do not want is substructures of R2. Okay, so what do we know about R2? It's linear substructures of R2. So what do we know about R2? R2 is, we're doing linear algebra. So there should be an invariance under scaling. So if you have something like this, some gap, then this wouldn't be closed under scaling, right? You want to be closed under addition, because that's kind of the second thing you can do in for vectors in R2, and this is not closed under addition. If I would have a vector here and I would have a vector here, then whatever, roughly here would be the sum. So this thing is not good. This thing is not good. This doesn't contain kind of the trivial elements, so you don't have an inverse, so this is not good. And this is just really, really bad because it already doesn't look linear, right? This just doesn't. So a substructure, a linear substructure of a linear space should be something that is preserved under the operations, most crucially scalar multiplication and addition. And all of these look really, really bad if you think about it in those terms. They are substructures in some sense, absolutely. So the right-hand side is kind of certainly in whatever topological sense, it would be a subspace or whatever. This is not too bad. The left side, just missing the origin. Otherwise, it looks pretty close on everything. usually called an affine space, whatever. So in some sense, these are substructures, but not in the sense we are looking at. And that's exactly the crucial point. So you're really starting with type XYZ, and you want to preserve being of type XYZ. That's the whole idea. Okay, let's really look now carefully under linear operations. That's what we do. We're doing linear algebra, right? So there will be basically two things. You can scale everything by a vector, or you can add two vectors. And if you think about it a little bit, um, then scaling by a vector just means whenever a vector is inside your space, oh, this was really bad. So here's my little vector, it's in red. Whenever a vector is in my space, and all scalar multiples are in my space, so whenever a vector is in my space, a whole line through that vector is in my space as well. That's just being closed under scalar multiplication. Addition is not much different. It's a bit, it goes kind of one dimension higher. If I have a vector in my space and I have another vector, let's say I have a red one and a blue one, then kind of the sum should be in there. Maybe green is a bad color. Orange, that's roughly here. And then the sum of everything should be again inside, and so on and so on. You play this game. As soon as you have two vectors, you basically get the whole plane where those two vectors lie. Right? And by the way, this is really just a plane. It looks like a, what is it? A hexagon, but it's just a plane cutting a cube. So in this picture, I've just cut out a cube of R3, and the corresponding plane is a little bit, well, it's a little bit tilted. So if it cuts, so here's a plane. It cuts this thing, and what you see is a hexagon. But don't be confused by that. It's really just a plane. All I'm saying here is, as soon as you have two vectors, and let's say they're not already on the same line, then you get the whole hyperplane, or the whole plane where they live in, just by assuming that they're closed under. So those were my type XYZ operations. Just that they're closed under those two things will force the whole line to be in it, and kind of the whole plane to be in it. Okay, makes some sense. So let's have a look at another example. So this looks like a sequence of linear subspaces. So a linear subspace, okay, the origin itself, that's a linear subspace. So this is here, this one. Yeah. Okay, any scalar multiple, it's a boring example. Any scalar multiple is in there. It's because it's just a zero, right? 0, 0, 0. Okay. And you can add it to itself. It doesn't change. So yeah, that preserves the property of being a linear subspace of the type XYZ, the linear type. A little bit more exciting. Of course, this is kind of a boring example. And there's another boring example. It's a bit more exciting, but it's still boring. The whole space itself is also a subspace. Those are usually called the two trivial subspaces. Because, yeah, sure. Yeah, there's not much to say about it. It's just, yeah, okay. More exciting are really the other ones. So here, my purplish one is just a vector and with it its whole line, because that's what's happening. If you put one vector and you want it to be a linear subspace, then you get the whole line through the vector. And it's of dimension 1, and it contains the origin. So it already contains the other subspace. What I did then is I took the same vector, but I took a vector not lying on the same line. So now by addition, you get the whole hyperplane. So now we have this two-dimensional space. So here, this is still the line from before. Of course, it's in there because it was already there before. And the other line goes in a different direction. Something like that. Doesn't matter so much. And by addition, you get the whole plane. And yeah, so this is, yeah, and this is just all of them by definition lie in this case in R3. So here's my trivial one. Here's this one. And those two. It kind of gets bigger and bigger. but all of them are linear subspaces, right? They are point, okay, point, trivial example, a line, a plane. The next one would be a three-dimensional plane. That's what's called a three-dimensional plane, and so on. And if you write down the formal definition, it's actually not so bad. So what is it? It's a subset, sure. Otherwise, I wouldn't call it a substructure anyway. It shouldn't be empty because, yeah, I mean, empty is just stupid, right? And the crucial property is that it's whenever you're inside of your space and you perform the operations that you know, you still be inside of your space. Formally, in formulas, if you have v and w in w and subscalars, then the sum and the scalar multiplication still um, is still in w. And the point why you do this is that W itself will still be a vector space. Considered by itself, not considered as a subspace, considered by itself, living in a vacuum, it's still a vector space. And that's the whole point about substructures. If you consider them by themselves, then they are still whatever type you start with. Yeah, that's kind of the main idea. So let me a little bit go back to this example. So there's a funny notion of a flag, and flags are very useful in linear algebra. They turn up implicitly, for example, in for Jordan normal forms. And there are flag manifolds, flag whatever. And the flag is funny. I have no idea who named this a flag, but basically it's the idea that you have a point in a line, in a in a hyperplane, in a planes, and so on. So it looks like a flag. Anyway, so strictly, well, it's just the following. You start with nothing and you end with the space. You end up, let's say, r to the n, and you have a v1, you have a v2, you have a v3, and all of them increase in dimensions. And that's what's called a flag. So you have a point and a line in a plane, in a hyperplane, in a hyperplane, whatever you want to call it. Right here you go. You have a point in a line, in a plane, in a hyperplane, and so on. Here's another example. You have a point in a line, in a plane, in a hyperplane, and so on and so on. Right? And so you always get those nested sequences of subspaces. Okay. Just to wrap up, a subspace is basically a subspace of anything, of type XYZ, is basically you pick it out, consider it in the vacuum, and it's still of the same type as it was before. And for a vector space, it's just this idea that subspaces are those linear sub things, lines, planes, whatever, in your spaces. Okay, I hope that was reasonably helpful, and I hope to see you next.